In this tutorial, let us calculate elastic constants with classical force field methods using LAMMPS. We will use the same zirconium metal as the example. Open the zirconium structure by File, Open, and then File from Disk. Since classical molecular dynamics simulations require more atoms and hence larger supercells, we will build a supercell by going to Builders, then Build Supercells. Click Custom, and then enter 700 for the first row, 480 for the second, and 004 for the third row. This will build an orthorhombic supercell with roughly 2.2 nanometers along each dimension. Next, we will assign a force field for the calculation. Click Force Fields, then Read. Navigate the directories using the arrow on the top right corner. Click on Metallic, then choose the Joe 2004 FRC force field by clicking Open. Click Job Control and then New Job to set up LAMMPS calculation using the flowchart interface. Right-click and choose Clear to clear the previous stages. The procedure is similar to using VASP. We first optimize the zirconium structure, then perform the elastic constant calculations. Click LAMMPS to add a LAMP stage. Double-click to edit. Click to add initialize lamps and minimize stages. Double-click the minimize stage to edit. Then choose anisotropically for relaxed cell. Then check the boxes for fix the cell in the YZ, XZ, and XY directions to fix a supercell shape and only relax the supercell volume. Click OK to close. Then click OK again to close the lamp stage. After the lamp stage, add a mechanical properties stage, then double-click to edit. Click the Flowchart tab, add a lamp stage, then double-click to edit. This time we will add the same initialize and minimize stages, but we won't relax the supercell volume. Press OK to close all the sub-flowcharts. Give the job a name and click Run. While the job is running, check its status through Medea's Job Control menu. Once the job is finished, click on Job Out to examine the computational details. You'll see the results on elastic constants and moduli, as well as other properties derived from the thermodynamic variables, such as the speed of sound, heat capacity, etc. This table compares the elastic constants from our classical force field calculation using LAMMPS to DFT and experimental values. This table compares the elastic constants from our classical force field calculation using LAMMPS to DFT and experimental values. The agreement with the experiment is good, but not as good as DFT, which is due to the nature of fitting empirical classical force fields. The advantage of using classical force fields is the computational cost, which took only less than 100 seconds on one core, compared to more than 12 minutes for DFT, which was also on one core.